Okay, everybody, we are here for a video on special relativity. We are going to take a qualitative approach to that, or to this video, but special relativity. I am, um, I'm going to do my best on this video to explain this. Just in general, it is so hard to explain this topic. It is so hard to communicate everything that needs to happen. So, more than happy to answer questions. Please just shoot them my way. Um, Absolutely happy to talk about those. But this topic, yeah, I'll do my best on this video, but let's continue this discussion when I see you next time in class. Okay. Special relativity. This is a concept that was put forth by, you guessed it, Albert Einstein, to kind of explain how the observations that scientists were making in the early 1900s didn't make sense with the other observations that we had made previous to that. Because at that time, we were just starting to get equipment that was good enough to really analyze and see things from the perspective of things that were moving almost or somewhere close to on a fraction of the speed of light. So as we were getting these instruments that were measuring these things, there were questions being put forth of those don't make sense. Um, so I'm going to give you a little bit of background here as to the speed of light. Then I'll just give you a quick introduction to what the history is called. I don't want to go over that whole the whole history of this quite in this video because it's not super relevant to the AP test. But I will drop the name for you to go explore on your own if you are so inclined. Okay, so special relativity. We are going to take a look at light real fast. All right, light. Remember, light is an electromagnetic wave. So if we are going to take this electromagnetic wave, that means it has an electric component and a magnetic component of this wave oscillating back and forth. So if we look at this, then we have, let's say we start up here with an electric field. And I'll just fill this in with straight up and down or relatively straight up and down lines. For our electric field, right, this is starting at the top. So maybe this is our cosine wave. But as this electric field starts changing, what does it induce? Well, it induces a magnetic field. Right? Electric field is constant right here, so there's no magnetic field. But over here, we have electric field changing at actually a pretty high rate. So right in this area here, that means we will actually have like a pretty decent magnetic field. And we will I'll draw it this way. Hopefully you kind of get the perpendicular nature of these two waves. Right, but then as our magnetic field is kind of plateaued, our electric field is zero, but then so zero electric field means the magnetic field will come back down. So our magnetic field's coming back down. I'll redo that real fast. But as the magnetic field comes back down, what happens to the electric field? Well, the electric field, changing magnetic field induces an electric field. So now we have this electric field because of the changing magnetic field. So that is, and I'm trying to layer these here so you can clearly see what is on top and what's on bottom and all that good stuff. Oh, I guess I could just redraw the red lines all on top. But right, we have a changing magnetic field gives us an electric field. A changing electric field gives us a magnetic field. All those kinds of good things. And then this keeps happening back and forth, right? We've got the zero electric or unchanging electric field, so zero magnetic field. So then the electric field comes back down to zero, but then as that's changing, right, the magnetic field starts getting induced. So we get a magnetic field induced in this instant. All right, and this just keeps happening over and over and over. Magnetic field comes back down, and that change in that magnetic field starts inducing an electric field. La-di-da. Okay, so we're kind of getting to the point where this is more of a repeat process than anything, and I don't want to waste our time on this. But right, we have these And I'll kind of give ourselves these waypoints or these markers, right? These pairs of points that are kind of overlapped, where one's at a max and one's at zero, all these kinds of things. Okay. But as this is happening, right, light is this kind of a deal where the electric field, the magnitude of the electric field, and the magnitude of the magnetic field are not equal to each other. Right? They are related, but they're not equal to each other. And they're actually given by this equation: E is equal to B. And if electric field, if that's in volts per meter, and if our magnetic field is in Teslas, then this is given by E equals B times C, where C is 3 times 10 to the 8th meters per second. So meters per second, and specifically 3 times 10 to the 8th meters per second. Okay. And this is just a relationship that we found to always be true, where this is always this C, this is always this 3 times 10 to the 8th. Right? That only happens because there's, right, a changing electric field will only change the magnetic field at a certain rate. It can't change faster than that. And then the changing magnetic field will only change the electric field at a certain rate. It can't change faster than that. And that kind of that speed at which they induce each other is C. So this means, right, and light doesn't require medium. Actually, it can only slow down when it hits mediums, right, higher indices of refraction. Since light doesn't require medium, that means that C is as fast as it will ever get. It's as fast as light ever gets. This leads us to the conclusion that light always travels at C, at least through a vacuum. So now we're going to be only using light traveling through a vacuum. So at C, at the speed of light. So we get this: C is equal to 3 times 10 to the 8th meters per second, right? This is approximation. It's 2.99 something something. But it's pretty close to 3 times 10 to the 8th meters per second. Okay. If you are interested in looking up more of the historical discovery of this light being constant, there's something called the Michelson-Morley, and I hope I spelled that correctly, the Michelson-Morley experiment, um, that uses interference of light waves to take a look at whether the speed of light was identical vertically or left and right, as they had some sort of setup rotating around the earth, which they knew was a pretty decent speed. And they came to this conclusion that the speed of light is constant always. It doesn't matter whether you're moving left and right or whether you're just stationary. Whatever it is, speed of light is this thing that is just always constant. So that's this Michelson-Morley experiment. If you want to look up what that is, it's awesome to kind of dive into the history of it. But it is pretty intricate, so be prepared for a deep dive. And you are at the level where you can understand it, though, completely. You can for sure understand everything they did as far as interference goes, reflections, refractions, transmissions, everything like that. But a couple of really smart people right there that gave us this conclusion: C is always the same. Okay. What we can see from this, let's go ahead and I'm going to make an analogy here. All right, let's say I'm riding a train. Okay, you got a train car, right? Another train car, whatever it is. Maybe that train car is now attached to, and I'm going to absolutely butcher this. Choo choo. Oh no, it just deleted everything I drew. Hold on, my apologies. So if we got a train, right, and let's say we're in the engine room, right? Cattle grade up front, all that kind of good stuff. But engine room, we've got a little dude right there. Let's call him Albert for, Albert Einstein. Okay. Smokestack. Yay, all that good kind of stuff. So if we have this train, let's say Albert right over here. Let's say Albert took a ball. Actually, before we do that, let's say our train is moving at 20 meters per second. Right? Okay, so this train's moving at 20 meters per second. Let's say now that Albert takes a ball and throws it forward for him at 10 meters per second. Well, what does that mean, right? That means we take the movement of the train and the movement of the ball relative to the train. So it's already moving at 20, and then we give it an extra 10 meters per second. So this ball will now be moving at 30 meters per second. All right, likewise, if Albert throws this ball backwards at 10, it'll be moving at a total of 10, right? Because we were moving forward. We took away 10 by throwing it backward. Um, so here's right kind of this train analogy, and you can see this right when you're driving in your car. You can throw a ball up and it comes right back down. It doesn't. You don't throw it up and then it shoots right back backwards. That just doesn't happen. Um, so that's kind of this initial thought of relativity. It's things related to each other. I'm going to real fast take a moment to define some terms. I'm going to define this term called inertial reference frame. An inertial reference frame. Okay. Now you've probably heard the term reference frame before, right? That's a way to think about things, or someone's perspective is reference frame. But what happens when we throw on this word inertial is we add these couple of physical rules or physics rules. This means one, that frame is not accelerating. So we have this frame that is not accelerating. That's what we mean by inertial. It has a constant inertia, um, right, moving at the same velocity. And we have to clarify that the laws of physics always apply. Right, the laws of physics apply within one specific inertial reference frame. We get these laws of physics that apply, but that includes that the speed of light, I apologize. That includes that the speed of light travels at 3 times 10 to the 8th meters per second. That's one of the laws of physics. Okay. The other thing this means by laws of physics, right? The most basic things like velocity is distance over time. Things like that, forces, whatever. Okay. Now, let's say we take our train, and I'm going to simplify our train drawing right here. Let's say we take our train, and now instead of the train moving at like 20 meters per second or some sort of speed that we actually have an idea what that looks like, let's say we have our train moving at half the speed of light. All right, really fast train. You'd get anywhere you want to very quickly, but it doesn't matter. Most of the time, this is put in the frame of either a train or of a spaceship, anything like that. Let's just do train for now. Doesn't really matter all that much. Okay, so we have our train moving at half the speed of light. What happens if I take a flashlight? All right, if I were to take a flashlight and shine light forward off the train. Well, right, light travels at the speed of light. So, right, just like we had with the train before, we're moving at half the speed of light here, but then we throw something forward at the speed of light relative to us. What do we expect, right? We expect this light to be traveling at 1.5 times the speed of light. Wrong. That is not possible, right? The speed of light is this physical speed limit. Nothing can move faster than that. So we have the speed of light that we cannot surpass. So then how do we reconcile the situation? Right? This observer, Albert, on our train here, Albert sees himself throwing forward light at the speed of light. But what happens? What were to happen if maybe I say you are sitting right there? Well, you are seeing this light come in, and it's light, so it's moving at the speed of light. So Albert sees this as the speed of light, but you see this as the speed of light. However, he's moving at half the speed of light, so you don't see the same things that he does. Weird. Okay, but how is this possible? Okay, let's put this in terms of let's give it a different situation. Let's say we've got a different, or not different situation, but an adaptation of it. Let's say that Albert has a set of mirrors, right? Mirror for both of those mirrors. If our Albert dude has a set of mirrors, um, let's say he shines light this way, or even is just looking at his reflection. Right? He's got a photon of light, bounces down, hits this mirror, bounces back up, and then it would hit this and continue bouncing forever, la di da. But let's just track to and fro. Let's say that takes some amount of time because it's moving at speed of light c, and right, this is, let's say each one of those is d over 2 is some distance over 2, so it travels a speed of d. Okay, right, and that uses this assumption this is d over 2. Um, okay, so we're traveling at a speed of light. It moves some amount of distance in some amount of time, right? So we know velocity is distance over time, right? Because we set this parameter that inertial reference frames, laws of physics apply, so we know that for sure. But what happens, right, as Albert is on this train, and I'm actually gonna give us more space here. Albert is kind of on this train, and Albert is taking this mirror, or this set of mirrors, right by you. Okay, you. Actually, I might do a little like, what's going on? All right, this is weird stuff. So Albert releases this dot, or releases this photon. So the photon is aimed for the other side, right? And I'll zoom in, right? Photon is aimed for the other side, but what happens as, right, it takes some amount of time to cross that d over 2, takes some amount of time to cross that distance. In that amount of time, Albert has moved over here. So it takes this amount of time for Albert to, or for the photon to get all the way across to the other side here. And I'll just use these so I can get a little bit straighter lines. Okay, so it's taken some amount of time, but now Albert has shifted. And then for that photon to bounce back, right, it's going to want to bounce back. But in the amount of time it takes the photon to get back up here, Albert has now moved again. So Albert is now up here. So when we draw our straight line from that point to that point, right, we see that. And Albert's now up there. I'm sorry, the light is now here while Albert has moved side to side. And you are just up here looking a little bit bewildered because how could this possibly be? Right? Light travels at c. Light travels at the speed of light. And we know that because the laws of physics must apply, it's distance over time. But in this case, it's not d, is not the distance that we've traveled. The distance we've traveled is not d. And it, right, because light is different, and here I'll actually do this way. It's not the distance d that we've traveled, because right, d is just to and fro. That's d, is to and fro. But we didn't go to and fro. We went to and way over, and then we went fro and way over again. So we've gone, and I'll call this just capital D is our new distance. So speed of light, now we've gone capital D. But right, this little distance took some amount of time t, and why not? Let's call this t1. Okay, so let's call that t1. So it can't be t1, right? Because it takes the same amount of, it's the same speed of light to travel both situations, but it's not the same distance, so it can't take the same amount of time. So we have to take some amount of time t2. Right? We have to take this different amount of time. And actually, since our distance increased, right, since we know speed of light has to be a constant, right? If distance increases, what does that mean about our time? Our time has to increase. Okay. So, right, we know this equation, velocity is distance over time. Well, our velocity can't change. So what are the only things left? Distance and time. Right? Because Albert was moving relative to you, Albert actually experienced some amount of time t1. So Albert experienced some amount of time t1, and you experienced some amount of time t2. So you experienced more time in this same event, right? The photon bouncing back and forth. Same event, but for you, the photon moved all this way. You experienced more time than Albert experienced. This is kind of the interesting part of what we can see from this thing called special relativity. Right? Relativity happens because you experienced more time than Albert experienced. So what that means is maybe Albert went through 1 second, and maybe you went through 5 seconds. So you are now older than Albert was. So there's something called the twin paradox, where let's say that we have, right, let's say we're on Earth, and let's say we have twin A stays on Earth, but then maybe twin B, uh, right? We like ovals, and then we've got the little fletchings, right, for rocket ship. Let's say twin B is an astronaut. Sorry, my pen is giving me fits today. Twin B is an astronaut. Yay. Okay, so we have twin B is an astronaut. And in this twin B astronaut, right, they're over here. Oh, goodness sakes. So twin B, they leave. Whee! Okay, they've left. They are now gone. Right? They've left, but let's say that they're traveling at like the speed of light. Right? I'm terrible at drawing, so I'm just going to use a box. Okay, so we've got twin B. They are now traveling. Let's say they're moving at most of the speed of light, like 0.9 c or something. Right? When twin B comes back, when twin B eventually returns, twin B will have experienced just like Albert, right? Twin B is moving, twin A is stationary. Albert is moving, you are stationary. So Albert experiences less time than you do on the Earth. So what this means is twin B has experienced less time. Twin B has experienced less time than someone who is on the Earth. They've experienced more time. Right, twins are born basically at the same time, maybe a couple hours apart. But when twin B comes back, twin A might be 5 years older. Maybe twin A is 5 years older. Twin B might have experienced like a year based on seconds and hours, right? And we'll define seconds as, right, the amount of time it takes light to bounce and then bounce back, because light is constant. So that's the only thing we can really use is the speed of light, because that's the only thing that's constant. So maybe twin A is 5 years older when twin B comes back, because twin B was traveling faster. That's something called the twin paradox, and this is something that we've observed. The twin paradox. This is something we've observed, and this is something also the movie Interstellar does a spectacular job of demonstrating. There's one scene where they have to go down to a planet that's near a black hole, and because you rotate so quickly when you're near the center of a galaxy, because you rotate so quickly, you are moving close to the speed of light. So you experience, right? You're the one who's moving, so you're the one who experiences less time. So that's why they say every second is maybe 5 hours for someone else, or for their loved ones back home. So that's how he goes back, and he's maybe a year or two older, but his daughter is all grown up. His daughter's like 30 something. So that's because of this twin paradox. You are moving, you experience less time, as opposed to someone who is stationary, they experience more time. Okay. At this point we're hitting a bit over 20 minutes on this video. I'm going to split this video into two sections, so to be continued on the next part. All right. Go back and rewatch what you need to. I know this is mind-boggling stuff, but here you go. Here's the end of part 1. Look forward to part 2.